Okay, so we're going to finish up this section about trigonometric identities. We talked about the Pythagorean identities. So let's just remind ourselves what those are, right? You should have these in your notes somewhere already. And you should start memorizing them. That'd be really good. You should do that. So what we know sine squared plus cosine squared, right, equals 1. And likewise, that means sine squared is 1 minus cosine squared, or cosine squared is 1 minus sine squared. If we divide everything by cosine squared, we get tangent squared plus 1 is secant squared. And then if we divide the top one again, everything by sine, we get 1 plus. And again, it doesn't matter because apparently I can't write and talk at the same time. Because addition is commutative, meaning it doesn't matter the order. I just put the 1 there because it's easier when I look at this. When I go to divide by sine squared, I can see sine squared divided by sine squared is 1. So I wanted to, I'm pretty much done with those identities. I just wanted to do one more example that I didn't quite get to. And I put some of these on your homework, and it's about this idea of a substitution into an expression. So I'm just going to do a quick example. So let's let x equal 4 secant of theta in this expression. Here's the expression, x squared minus 16 all over the square root, of x squared minus 16. And then what I want to do is I want to, kind of my directions are going to be, so use, let x equal that, use this substitution. To express, or to rewrite, let's say, in terms of trigonometric functions. We'll just call those trig functions. A couple things we have to make sure we assume here. Sometimes we have to assume some things. We're going to assume that theta is in the first quadrant. Okay. And this example seems kind of random, but it's really not. This is something that when you get to calculus, we're going to do quite a bit. So if you can see it now, when you get to calculus and you're, Calc 2 probably, when you're evaluating integrals using trigonometric substitutions, if you've seen it already, it'll just make it that much easier. So I'm going to take this expression here, x squared minus 16, all over x squared, and I'm going to use this substitution that they give us. Okay, so everywhere I see an x, I'm just going to put 4 secant of theta. So I have 4 secant theta squared minus 16 all over 4 secant 4 secant of theta quantity squared. Don't you dare cancel those 4 secant thetas. You cannot do that. Oh, don't even. Can't cancel that because of the square root. You can't cancel it because of the minus. You just can't do it. Don't do it. Don't do it. All right, so let's see what happens here. So I'm going to get under the square root. If I square that 4 secant theta, I'm going to get 16 secant squared theta minus 16 all over 16 secant squared theta. And I'm going to run out of some room here. I'm going to start over here. That's kind of poor notation, but so don't square root over the subtraction sign. You can't do that either. You're like, Sarah, why would you ever do that? Oh, I've seen it, guys. I've seen it. I know how you think. I know what you want to do. I can factor out a 16 though. Whoa, all over 16. I did not give myself enough room here. And the whole reason we wanted to do this is what this allows us to do, like when we get to calculus, it takes something that is quite complicated and it's going to change it into something that's a little bit easier to deal with. And that's secant squared minus 1. If I look up here at my Pythagorean identities, and if I solve this for tangent squared, notice that I can see that tangent squared is equal to secant squared minus 1. So that's going to help a lot because what that's going to do is get rid of our square root. So now I have the square root of 16 tangent squared of theta all over 16 secant squared theta. Now I'm going to need some more room. So Let's go to a new layer here. All right. So we had, remember we had a square root of 16 tangent squared theta all over 16 secant squared theta. So now I can square root. So the whole reason they gave us that fact that theta was in the first quadrant is that means that the tangent of theta is going to be positive. Because you guys, you got to be a little bit careful when you're taking the square root of x squared, because this guy equals x as long as x is positive, but this guy actually equals a negative x if x is negative. So that's why they kind of tell you where theta is, so that when we square root that squared, we know it's going to be just tangent of theta, because tangent of theta is positive. So we're good to go. All right, so I got rid of that square root. I have 4 tangent theta all over 16 secant squared. I can cancel this now because it's all multiplication. You know, and I'm going to bring that 4 in the denominator out as a 1/4, and I'm going to kind of see what happens here. So tangent is sine of theta over cosine theta, and secant squared is 1 over cosine squared theta. And I write that in terms of sine and cosine to just be able to see how I'm going to simplify this. So the numerator then is sine theta over cosine theta. And then the denominator, I'm going to flip it and multiply. So I get cosine squared theta all over 1. I can cancel one of the cosines and I get 1/4 sine theta, whoa, cosine theta. All right, guys, and that's it. I'm done. That is rewriting that expression, which started off in terms of x's, rewriting it into something in terms of trig. Really, really helpful when you get to Calc 2 to take integrals using trig substitutions. And why are we doing it here? Because we want you to practice it, because it's all trigonometry and you want to practice it. All right, so we are moving on to the last part in this section, and the last part in this section is going to be talking about the sum and difference formulas, as I like to call it, sum formula. We're gonna figure out sum formula. Sum, SUM. I know it's not funny, but I find it amusing. So I guess, so the question is, if I were to take the cosine of, let's say, 30 degrees plus 60 degrees, does this equal the cosine of 30 plus the cosine of 60, right? So when we talk about these sum and difference formulas, the motivation for this is, can I have a formula if I want to take the cosine of 2 angles added together or the sine of 2 angles added together? How do I do that? So your first gut reaction might be to just distribute the cosine, right? We learn distribution all the time in algebra when we're first learning about numbers. And let's see if that's going to be true. So if I work with this side here, right, this whole thing, this is 90 degrees. And so I'm sure you will agree with me that because 30 plus 60 is 90, this becomes the cosine of 90 degrees. And what is the cosine of 90 degrees? That's 0. So look at what I've hypothesized here. I've said, well, what if I'm taking the cosine of 30 plus 60, is that equal to the cosine of 30 plus the cosine of 60? If it is equal to that, then when I do this, I better get the same thing over here, right? Because all of these steps right here we agree with. We know that the cosine of 90 degrees is 0. We know that 30 and 60 is 90. Over here, what part have I guessed on? I've guessed that I could distribute that cosine basically through to each one. We're going to see quickly that this is not going to be the case. Cosine of 30 is root 3 over 2. Cosine of 60 is 1/2. So last time I checked, 0 is not equal to root 3 plus 1 over 2. So what I'm trying to show here, I really need you to understand that we cannot take the cosine of alpha plus the cosine of beta and set that equal to the cosine of alpha plus beta, okay? Don't do it. We can't do it. We cannot distribute cosine. This cosine here, this is a function. It's kind of an operation that's happening to those angles or the real numbers. So we can't just distribute. Just like before when we had like natural log of x squared plus 1 or something like that. You could not distribute the natural log across each one. Maybe you didn't know that. Now you do know that, or maybe you don't remember that. But that's not true. That's the same with the trig functions. We can't do that. So we need to figure out how are we going to add to numbers together, or can we find an expression for figuring out how to do this? And we can, and let's kind of go through the derivation of this formula. All right, so stick with me on this. So the first thing we're going to do is remember if we're our definitions of sine and cosine, when we talked about radians, really just had to do with the arc length, right? Oh, that y-axis is going to bother me. The arc length in a circle. So that's going to be kind of my motivation for this. Oh my goodness. Okay, so we have a circle, and we're just going to consider in the first, in the top half, so 0 to pi, and without loss of generality is something we kind of say in math, meaning it's okay if I just consider it in the first half. This will hold for any of them. So I want to consider two kind of angles, or two radians, really. So let's consider this distance right here. I'm going to consider this distance right here. I'm going to call this u. Okay, and then I'm going to consider another distance, maybe a little bit smaller than that, and I'm going to consider this distance v. Okay, so the v is the yellow. And if we look at the points that it makes on this circle, right, we have determined that this point right here would be cosine of v, sine of v. Remember, that's when we had our whole discussion about the unit circle. And then this point right here will be cosine of u, sine of u. Okay, and then I'm going to make one more definition, and this definition is going to be kind of important. I'm going to call this distance right here, you can see in the gray, between the points u and v, I'm going to call this s. And clearly s, if you look in this case, is just that whole distance u, but take away the v part. Okay, so that distance s is just going to be the difference between the arc length u and the arc length v. I have a point to this, I promise. So let's look at these 2 points, this purple point and this yellow point here. What if I were to find the distance between these 2 points right here? So I'm going to just call this distance, let's say those, that's a point A and a point B, but I'm just going to call this distance AB. Okay, and the distance formula, AB, remember what the distance formula does? You take your difference in x values, okay, so like cosine of u minus cosine of v, so it's x2 minus x1, quantity squared, plus y2 minus y1, so sine of u minus sine of v, quantity squared. That's just the distance formula, and I'm just using my x value and my y values, right, for the points that I know I'm at. This is why we had to do this in 2, because this takes us a little bit. So I'm going to go ahead and FOIL this out. So AB equals square root of, if I FOIL this out, I get cosine of u, cosine squared of u. Outside and inside, right, are the same, so I have 2 of them. Cosine u, cosine v. I'm going to run out of room. I'm just going to tell you that right now. Then plus cosine squared of v. That's that guy FOILed out. And then likewise, I'm going to get a sine squared u minus 2 sine u sine v plus sine squared of v. This is all under the square root. And now look at what's kind of cool about this is if I have a sine squared v plus cosine squared v, that's going to give me 1. And then I have cosine squared plus sine squared of u, that's also going to give me 1, which is good news. Okay, so now what I have is I have those 1s added together. That's 2. And then I have these guys left over. So notice they both have a -2 there. So I'm going to go ahead and factor out a -2. And what that's going to leave me with is cosine u, cosine v, minus sine of u, sine of v. Okay. Nope, plus. Sorry about that, plus. I factored the negative out, plus. Okay, so let's kind of keep that in the back of our heads here, that is one way to describe AB. Now, the other way I could describe AB is I could take, this is going to get a little convoluted here, but I could take this point right here, right, which is basically V, and I'm just going to rotate it, and I'm going to put it on the x-axis. So V basically has become the point 0, 1. And then all that's going to do is kind of do this rotation. And so U will end up maybe, let's say right here. But what do I know? I know that whatever this distance is right here, it's the same as S. Okay, and so what do I know about that point right there? That point right there must be cosine of S, sine of S, whatever that distance is. So again, this S right here, that value right there, that's going to be this distance right here, same distance. And now I'm going to do the same trick. I'm going to take AB. Remember this, that must be the same distance between these 2 points right here, correct? Correct. I feel like you're talking to me about that. So I'm going to take the distance formula again for that. I'm going to do the change in x's. So that would be cosine of S minus 0, quantity squared, plus my change. Oh, Sarah, you guys saw it, I bet, before I even saw it. Wow. Come on, Sarah. So that's 1, 0. My apologies. So I gotta fix a couple things here. That should be minus 1. Minus 1, and then plus sine of S minus 0, quantity squared. Foil this sucker out and look at what we get. I get cosine squared S minus 2 cosine S plus 1, and then this is, of course, plus sine squared S. And so I'm going to do kind of the trick that I did before. Cosine squared plus sine squared is 2, or excuse me, 1. And then I add this 1 to it, and that's where I get the 2. So I get 2 minus 2 cosine S. Oh my gosh, I hope you guys are sticking with me. I know this is complicated, but it's good for you to see proofs like this. So look at what I have, you guys. I have that AB, oh, whoa. I have that AB is equal to all this crap right here. It's not crap, but you know what I mean. And all this stuff right here. And remember, they're describing the same distance. So what I'm going to do now is I'm going to clear this layer, and then I'm going to equate those. So I know that those ABs must be the same distance. That means I know that 2 minus 2 times cosine of U, cosine of V, not enough room, plus sine of U, sine of V, right? That must equal the square root of 2 minus 2 cosine of S. Okay, and now square both sides. Look at what we get. I get 2 minus 2 times the cosine of U, cosine of V, plus sine of U, sine of V equals 2 minus 2 cosine of S. Those 2's are gone, guys. We're almost there. This is very exciting. I can divide each term by -2, each side by -2. And look at what I have, you guys. I have that the cosine of S. But remember, what was S? You remember. What was S? S was U minus V. Whoa. So I'm sorry, we're doing the subtraction before the addition. So cosine of U minus V then is equal to all of this right here. Cosine of U, cosine of V, plus sine of U, sine of V. So when I was talking about that cosine of U plus V, I'm sorry, I should have done U minus V, but how we can't distribute across the addition, it's the same with the difference when I have U minus V, and we've just proven that. We have just proven that it's obviously the cosine of U minus V isn't cosine U minus cosine V. It is the cosine of U, cosine of V, and then you add the sine of U times the sine of V. So if you need to go pause this and take a nap or something, I totally understand. It's a little bit crazy. But so that's what we know for cosine of U minus V. If we want to do plus, a really easy way to do plus is, well, so I'm going to kind of derive this for you, the plus. I'm not going to do that whole thing again, don't worry. But let's see what would happen if I wanted plus. So let's say instead of having minus V, I have minus a negative V. So I'm going to use this formula here. So this says to take cosine of the first angle, then take cosine of the second angle. So in this case, I'm going to do a negative V, okay, plus, then what does it say? Sine of the first angle, times sine of the second angle. And if you notice here, remember cosine is an even function. So the cosine of negative v is the same thing as the cosine of v. However, sine is an odd function. So what's going to happen? This guy right here is a negative sine of v, right? So that negative will just come out there. So I get minus sine of u, sine of v. So when we go to find that addition, right, look at here, I have a minus and negative. So what does this tell us? That the cosine of u plus v, now I know what the cosine of u plus v is. It's the cosine of u, cosine of v, minus, excuse me, cosine always has the opposite sign. We're going to see sine has the same sign, which is kind of nice. Sine of v. So this is my sum formula. It's sum formula for cosine. It's how I take the cosine of two angles added together. This is my difference formula, or how I take the cosine of two angles, the difference of two angles. Okay. So let's do a quick example, and then I want to show you sine. So, and then we'll kind of write these all. We should write these all down, don't you think? I agree. Let's do. I don't need the graph. So let's just look at a quick example. So, for example, what if I wanted to find the exact value? Find the exact value. So don't put this into your calculator. I want to find the exact value of cosine of 15 degrees. Okay, so what we can do with this is we can use our sum or a difference formula. And I mean, it's fun kind of to do this, or fun might be different. It's fun to kind of do this with an angle, but honestly, these sum and difference formulas are going to be used a lot more when we actually like simplify more expressions, or when we solve some trigonometric identities. But cosine of 15 degrees, if I want the exact value, your goal here is going to be to write 15 degrees using 30, 45, or 60 degrees. That's what we want to do. So how can I write 15 degrees using 30, 45, or 60? Well, or the sum or difference of those, I could take 45 degrees minus 30 degrees. Okay, and now we have this difference formula. Let's remind ourselves what that is. Let's just do a different color just to help a little bit. So the difference, cosine of u minus v. So remember, you're going to take the cosine of the first, cosine of the second, and then it's the opposite sign. So then I have plus sine of the first, sine of the second. So I'm just going to use this formula. So here then cosine of 45 minus 30, okay, is going to be the cosine. And show me these steps, you guys, because if you make a mistake and you don't show me any work, I can't give you partial credit. So if you accidentally decide that day that the sine of 45 is root 3 over 2, which it's not, but as long as you show me you're plugging this into the correct formula, I can give you at least a bit of partial credit for it. So exact value, right? 45, cosine of 45 degrees, first quadrant, so it's root 2 over 2 and it's positive. Cosine of 30 degrees is root 3 over 2, plus sine of 45, also root 2 over 2, but sine of 30 is 1 over root 2. And if you simplify this, this is root 6 over 4, and this is root 2 over 4, so we just get root 6 plus root 2 all over 4. And now we have a way, as long as it's a sum or a difference of involving, 60, 45, or 30, we have a way of actually finding the exact value of those. Or, you can always put it into your calculator too. So, okay, and I'm going to go ahead, since we're already at 23 minutes, let's just go ahead and finish writing down all of these identities. The sine identity actually isn't too bad to do if you use the cofunction identity, where we know, that the cosine of theta is equal to the sine of 90 minus theta. If you use that, you can develop the sine and the cosine, the sum and difference formulas for sine and cosine and tangent. I'm going to let you look that over. You can look that over in the book. But let's go ahead and write down the sum and difference formulas. And I am going to give these formulas to you on the exam. I am not going to give you all of the identities. So I guess be thankful that I'm giving you these. So sum and difference identities, these I'll give you on the test, but you need to know how to use them. So I know I haven't proven the sine ones for you, but for sake of time, I'm just going to go ahead and give them to you here. So here's what sine does. So sine does kind of the opposite. You take the sine of u times the cosine of v, and then it has the same sign, S-I-G-N. So then it's going to be plus, and then instead of, so you take sine of the first, cosine of the second, and then you flip it. Then you take cosine of the first, sine of the second. So you do cosine of u, sine of v. And because multiplication is commutative, you know, you could have done sine of v, sine of u. So sine of u minus v. Okay, that same thing. It's still sine of the first, cosine of the second, but then it takes the same sign, S-I-G-N, and then you do cosine of the first, sine of the second. Okay, cosine we already found, but let's write those down again. Cosine of u plus v. You're going to do the cosines together, cosines first, then the opposite sign, and then the sines. If that isn't confusing you, man, props to you. Cosine of u minus v. Again, cosines first, cosine u, cosine v, but different sign, plus sine u, sine of v. Okay. The exact, so I'm going to do the identity for tangent. The identities for tangent, I'm not going to prove to you either. I hope you are okay with that. But the identities for tangent, you can use sine and cosine to kind of figure out those. But here are the identities for tangent. Again, I'm going to give these to you on the test, but you need to know how to use them. So tangent, you would expect maybe to have a fraction involved because tangent is sine over cosine. Tangent of u plus v is tangent of u plus tangent of v all over 1 minus tangent u tangent v. And these are kind of interesting to prove. You know, if you did sine of u plus v over cosine of u plus v, that would be tangent of u plus v. And then I don't know off the top of my head, but I think if you maybe divide everything by sine and cosine, you might get something like that. I wasn't planning on proving it to you, so I don't remember. So I should have just stopped talking because I imagine you are satisfied with me just writing these down for you. You know what? If you really want me to prove the sum and difference formulas for tangent, seriously, send me an email, let me know, and I would be happy to do that for you. If you can't sleep tonight without knowing why they are true, really, please let me know. Okay, so these are the 6 sum and difference identities. I'll be giving these to you on the test. Let's just do a couple more examples and then we will call it good. So 2 more examples. I think that's what I would like to do. I want to do one with tangent because tangent can be a bit weird. I don't know. I am pretty sure that, well, let's do a tangent. I'm going to stop talking really quick. So find the exact value. And let's pick one of, let's do the tangent of 195 degrees. Okay, so the tangent of 195 degrees. So this could be kind of tricky, right? So I need to find a way to rewrite 195 in terms of angles that have reference angles of 30, 45, or 60. So 195, so let's say like if I subtract 60 from it, 195 could be written as 135, right, plus 60. Would that work? Yeah, I think I could use this because what's this guy's reference angle? Its reference angle is 45 degrees. So I'll be able to do that, and I know the exact value of tangent. I could have also, when I first wrote this down in my mind, I was thinking of 150 plus 45. So you guys, when you do this, you guys might use different angles to find these values. But your answers should be the same. Okay, so I don't know, you can use either one. Let's do the 135 plus 60. So tangent, or you could try and do some subtraction too. You know, you could do like 220 minus 195 wouldn't work, or you know, you could find ones like that, or 220 minus 25 wouldn't work. But you could try and figure out. Oh wait, 240. So you could have done 240 minus 45 degrees, that would have worked also, and use the difference formula instead of the sum formula. So tangent of u plus v, remember that is tangent of u plus tangent of v, and then on the bottom it's the opposite sign, 1 minus tangent of u, tangent of v. I see it, I see it, I see it. Okay, so I'm going to use, what did I say I was going to use? Let's use a 135 plus 60. Okay, so I'm going to take the tangent of 135 plus the tangent of 60, all divided by 1 minus the tangent of 135 times the tangent of 60. Okay, so this should work out pretty nicely. Tangent of 135, so 135 has reference angle 45 degrees. I know that the tangent of 45 degrees is 1. I also know that because I'm in the second quadrant, right, the tangent of 135 is going to be a -1 because tangent is negative in the second quadrant. Tangent of 60, I know 60 degrees is √3. Oh, I meant to give you one, that's okay. That's sine over cosine, yeah, √3. I meant to give you one where you kind of simplify a little bit more, but we'll be good with this for right now. I get √3, and it's in the first quadrant, so it's positive. Then I'm going to have 1 minus, again, tangent of 135 is a -1, and then tangent of 60 is √3. Cool. So what do I get? I get a -1 plus √3 all over 1 plus √3. So not exactly the same, right? But a -1 plus √3 all over 1 plus √3. You could leave it like that. If I think my math lab is going to want you to rationalize the denominator. So I just want to remind you to rationalize the denominator. You multiply by the conjugate. I don't know. Try entering it without rationalizing it. Maybe it'll like it. To rationalize, though, I multiply by the conjugate of the denominator. If I FOIL this out, I'm going to get a -1, and then I get plus √3, so plus 2 √3. And then I get √3 times a -√3, that's -3, all over 1 minus 3. That's why you rationalize it, right? It becomes a difference of squares. And so what is our final answer? It looks like our final answer is a -4 plus 2 √3 all over -2. Divide each term by -2, and this is pretty nice, actually. We get 2 minus √3, so you should rationalize it. That's lovely. 2 minus √3 is our final answer for that. Okay, look at on the fun sheet, look at that one, because I have one where, you know, you get something like -1 plus √3 over 3 or something like that, and then you get, you know, 1 minus √3 over 3. And you need to do there is multiply everything by 3 to get rid of that complex fraction. That's the kind of the easiest way to do that. All right, you guys, one more example. Oh my goodness, 32 minutes. One more quick example, and then we'll call it good. I know I haven't done a whole lot of examples, but look at the fun sheet. You know, look in your book, and I'm sure you'll find that. So let's let the sine of alpha, some angle alpha, I don't know what it is, be 2/3 with alpha in, well, let me do kind of what your book does, with alpha between pi over 2 and pi. Okay, so it's in the second quadrant, pi over 2 to pi, and let cosine of beta, okay, equal, let's say, a -4/5 with beta. Let's say that this guy is in the third quadrant. That's not the third quadrant, people. All right. Let's find the sine of alpha minus beta. Okay. All right, so sine of alpha minus beta. So sine of alpha minus beta, if you look back at your identities, we take the sine of alpha, the cosine of beta, takes the same sign, so minus, then cosine of alpha, sine of beta. So look at the things that we know. What are some things we know? We know sine of alpha, right? So we're going to know this guy right here. And we know cosine of beta, so we're going to know this guy right here. So what do we still have to find? We still have to find cosine of alpha and sine of beta. So let's deal with alpha really quick. What do I know about alpha? Alpha is in the second quadrant, right? And I know, so this is my alpha. So go ahead and put an arrow there to show that that's alpha. And what else do I know? I know that it's the sine of it is 2/3. So if I draw my little triangle, well, I tell you to put the arrow in, then I'm not going to have room to write my hypotenuse. I know that this is 2 and this is 3. So if I solve, remember, I need cosine of alpha. So if I solve this, you know, I get 9 minus 4. So I believe that this is the square root of 5. You should check me on that. And it's negative because it's in the second quadrant. So just by throwing this into the second quadrant and doing a little bit with the triangles, I see that the cosine of alpha is a negative root 5 over 3. Okay? Now, let's see what's happening with beta, because I know I'm going to need sine of beta. So what am I given? I'm given that the cosine of beta, and I am in the third quadrant. Okay, so I know that the cosine of beta, right, if I look at my triangle here, I know I have a negative 4/5. So I know that this is negative 4 and this is 5. Well, that means this is a 3, 4, 5 triangle. So that must be negative 3. So the sine then of beta must be a negative 3/5. And now I did not give myself enough room. So what do we end up getting here? I think I can squeeze it down here. So then the sine of alpha minus beta, right, is the sine of alpha, which we know is 2/3. And I should have said find the exact value of this. Cosine of beta is a negative 4/5. Okay, and then I'm supposed to subtract the cosine of alpha, which now I know is a negative root 5 over 3, times the sine of beta, which I know is a negative 3/5. So what is my final answer here? I'm going to have a negative 8. Here I just get 3 root 5, right? So this negative stays, minus 3 root 5. And then we have the same denominator for all of them, which is 15. And that's my answer. Don't cancel the 3 and the 15. You can't do that because of that subtraction sign. All right. Oh my goodness, we're at 37 minutes. Really quick, if they're wanting you to find something like sine of 5 pi over 12, which I think I gave you some like that, you can figure out how to write 5 pi over 12 in terms of, you know, like something with a reference angle of pi over 4, or something with a reference angle of like pi over 3. But what I really recommend you just change it into degrees. Change it into degrees and then see how you can write it in terms of something with 30, 45, or 60. Whew. Good job, you guys. You hung with me. I'm proud of you. See you next time.